What is this bridge made of?
The bridge is made of metal.
Why do they use metal for making bridges?
Well, in olden times, people made bridges and buildings with wood. But none of these bridges and buildings lasted long. Structures that are made of metals or use metals to form the skeleton of the structure are strong and durable. That's one of the reasons why metals are used so widely for making almost everything that we see around us. In this lesson, you will learn about metals. By the end of this lesson, you will be able to list the uses of metals, list the physical properties of metals, and list the chemical properties of metals. Metals are used in making machinery, automobiles, aeroplanes, buildings, trains, satellites, gadgets, cooking utensils, water boilers, etc.
Are all metals hard, strong, and durable solids?
No. Sodium and potassium are soft metals that can be cut with a knife. And mercury is a liquid metal.
A liquid metal. Can metals be gaseous too?
No. There are no gaseous metals.
Dad, why are those thick wires carrying electric power made of metal? Is it because the wires need to be very strong?
Yes. Those wires need to be strong. But there is a more important reason why those wires are made of metal. You see, metals conduct electricity very well. Non-metals don't. That is the most important reason why wires that carry electricity are always made of metal. Haven't you noticed the wires attached to all electrical and electronic gadgets, such as toasters, television sets and computers?
Speaking of gadgets, why is the base plate of an electric iron made of metal? It is not supposed to conduct electricity.
The metal base in an electric iron is for conducting heat, not electricity. Metals are also very good conductors of heat too. That's why cooking utensils, irons, heaters, etc. are all made of metals. Besides, metals can be easily shaped into wires. This property of metals is called ductility.
Dad, what is that man doing?
He is a blacksmith, and he is hammering the red-hot piece of metal into a flat tool. Metals can be easily shaped into thin flat sheets. This characteristic of metals is called malleability.
Ah, that explains this aluminium foil that Mom uses to pack my lunch in. Dad, look at those shiny bells in the temple. Are those made of metal too?
Yes. All metals make a sound when struck with hard objects. And most metals can be polished to a shiny appearance. That's why gold and silver jewelry shine so much.
Dad, how do I distinguish metals from non-metals?
Well, as we just saw, things made of metal typically are sturdy, can be polished to a shiny finish, are good conductors of electricity and heat, can be drawn into wires and beaten into thin sheets, and produce a sonorous sound when struck with hard objects.
Dad, why has this iron rod turned like this?
It's rusted. Iron reacts with atmospheric oxygen and moisture to form iron oxide, which is commonly known as rust. Metals react with other elements in a variety of ways. Metals burn in the presence of oxygen to form metal oxides, which are basic in nature. For example, if you burn a strip of magnesium, magnesium will burn in oxygen to form magnesium oxide. Magnesium oxide dissolves in water to form magnesium hydroxide, which is basic in nature. Similarly, when a copper vessel is exposed to moist air, a green coating forms on its surface. The coating formed is a mixture of copper hydroxide and copper carbonate.
At last, I found them.
What are these? Oh, iron nails.
These nails got rusted too.
Yes, the nails have rusted because of the moisture present in air. Metals react with water, but all metals do not show the same kind of reactivity. For example, sodium reacts vigorously with water and oxygen and produces so much heat that it catches fire. That's why sodium is stored in kerosene, to prevent it from coming into contact with moisture and oxygen. Let's try an experiment. Take a trough. Fill half of it with water. Now, carefully cut a small piece of sodium and dry it using a filter paper. Then, wrap it in a small piece of cotton. Place the piece of sodium in the water trough. You will observe that sodium reacts vigorously with water, catches fire and moves about in the water, making a hissing sound. Now, touch the trough.
It's hot.
So, now you understand how much heat was produced in the reaction. When you introduce a red litmus paper, it turns blue, indicating that the solution formed is basic in nature. Be careful. You should stay away from the water trough during the reaction. It gets very hot.
What are you doing, Father?
I'm cleaning this tap with a lime peel. The tap is looking dull because of the deposits of calcium salts in water.
Ah, the tap is shining now. How did that happen?
Lime juice contains citric acid. Acids react with salts of metals. The citric acid of the lime juice reacted with the calcium salts on the tap, and now the tap is clean. Metals react with acids, such as hydrochloric acid and sulfuric acid, to give out hydrogen gas. Let's try an experiment to understand how this happens. Let's take 4 different metals: magnesium, iron, aluminium and copper, in 4 different test tubes A, B, C and D respectively. To these test tubes, we add 5 milliliter of dilute hydrochloric acid or sulfuric acid using a dropper. We now heat the test tubes gently using a Bunsen burner. Hydrogen gas is liberated. But how do we know it's hydrogen? To test the gas, we introduce a burning splinter near the mouth of the test tube. The splinter is put off with a pop. It shows that the gas is hydrogen. From this, we can conclude that metals react with dilute acids and liberate hydrogen gas.
Do metals react with bases in the same way that they react with acids?
Yes, the reactions are quite similar. Metals react with bases, such as sodium hydroxide, to produce hydrogen gas. Let's verify this with an experiment. Prepare a fresh solution of sodium hydroxide in a test tube by dissolving 3 or 4 pellets of it in 5 milliliter of water. Into this solution, drop a piece of aluminium foil. We now bring a burning splinter near the mouth of the test tube. The splinter is put off with a pop. This shows that hydrogen gas was produced.
Indeed, the reactions of metals with acids and bases are quite similar. But Dad, you mentioned that some metals, such as sodium, react more vigorously than others. How do you know that?
Let me show you an interesting experiment. Let's take 5 beakers, A, B, C, D and E. Let's take copper sulfate in beaker A and B. Drop some zinc granules in beaker A and iron filings in beaker B. Take zinc sulfate in beakers C and E. Drop copper turnings in beaker C and iron filings in beaker E. In beaker D, take some ferrous sulfate solution with a few copper turnings. Now, note that the blue color of the solution in beaker A has disappeared. This is because zinc replaces copper from copper sulfate. In beaker B, the solution turned green. This is because iron has replaced copper from the copper sulfate solution. There is no change in the other 3 beakers, C, D and E. This brings us to the end of the detailed session on metals, their appearance, behavior, and uses in our day-to-day life. Now, you should be able to describe the physical and chemical properties of metals and list their uses.
Dad, what are you doing?
I'm making a bonfire. Do you know that wood used for a bonfire is made of carbon, a non-metal?
A non-metal? What's that?
There is a class of elements known as non-metals. By the end of this lesson, you will be able to list the uses of non-metals, state the physical properties of non-metals, and list the chemical properties of non-metals. Look, to light this bonfire, I'm using a matchstick. The head of this matchstick is coated with phosphorus, a non-metal. The oxygen in the air that we breathe is another example of a non-metal.
Look, Dad, an orchard. What's the farmer doing?
The farmer is adding fertilizers to the trees so that the trees grow well and bear fruits. Fertilizers contain non-metals like sulfur, phosphorus, and nitrogen.
Why are you adding those tablets to that water?
These are chlorine tablets, which give out chlorine gas that purifies the water. Chlorine is another example of a non-metal.
Ouch! I've cut my finger.
Let me apply some antiseptic. Do you know antiseptics contain iodine, which is a non-metal?
Look, Dad, firecrackers.
The local villagers must be celebrating a wedding. Do you know that non-metals like boron, sulfur and nitrogen are used in making crackers?
I see that non-metals have a great deal of use in our everyday lives. How does one identify non-metals? Do they have any distinguishing characteristics?
Yes, like metals, non-metals also have typical properties, which may be categorized as physical and chemical properties. The physical properties are more readily observable in our daily life. Non-metals exist in all the three states: solids, liquids, and gases. For example, silicon and carbon are solids. Bromine is a liquid. Chlorine, fluorine, and oxygen are gases.
Wow! The aluminium packaging is shining.
Yes, but unlike metals, non-metals do not shine. They have a dull appearance. For example, the surface of sulfur and phosphorus do not shine. Try to break this piece of charcoal into smaller pieces.
I did.
Do you remember the blacksmith near our home hammering red-hot pieces of metal into flat tools? Metals can be hammered into sheets, but non-metals break into pieces when hammered.
What are you doing?
I'm trying to tie the tent using this piece of metal wire. It is stronger than a rope.
Can wires be made of non-metals too?
No, non-metals except for carbon fibers cannot be drawn into wires. They are non-ductile.
Why are we using a cloth to remove it from the fire?
This kettle is made of metal, which conducts heat very well. That's why the handle of the kettle is too hot to touch. Unlike metals, non-metals are not good conductors of heat. For example, sulfur and phosphorus do not conduct heat. Watch this.
Wow! I see the electric bulb glowing.
The iron nail is a metal, so it conducts electricity. Now, replace the iron nail with a piece of charcoal.
The bulb is not glowing.
That's because non-metals do not allow electricity to pass through them. Graphite, being a non-metal, conducts heat and electricity. This is due to the presence of free electrons. You hear that noise when I hit the nail with this hammer. Metals make a typical ringing sound when hit with hard objects. Try to hit this piece of charcoal.
It's broken to pieces.
Non-metals do not produce any ringing sound when hit hard, but they break into pieces. For example, carbon turns into powder when hit hard. When you make a bonfire, the wood burns to release smoke. Non-metals react with oxygen and form acidic or neutral oxides. For example, sulfur reacts with oxygen to form sulfur dioxide, which is acidic. Let's perform an experiment to understand this chemical property. Take a small amount of sulfur in a deflagrating spoon and heat it. As soon as the sulfur starts burning, introduce the spoon into a gas jar. Then, cover the jar with a lid to ensure that the produced sulfur dioxide gas does not escape. Remove the spoon after some time. Add a small quantity of water into the gas jar and quickly replace the lid. Shake the gas jar well. Sulfurous acid is formed. Now, introduce a blue litmus paper which turns red. The sulfurous acid turns the blue litmus to red. This indicates the acidic nature of non-metal oxides. From this, we can conclude that non-metal oxides are acidic in nature. Observe the bonfire.
Why?
In this bonfire, if there is a partial combustion, carbon monoxide is produced. This is a neutral oxide. Nitric oxide is another example of a neutral oxide. We don't need the fire anymore. Let's put it out.
The fire's gone, but the unburnt charcoal is left behind.
That's true. Generally, non-metals do not react with water, though they may be very reactive in air. Such non-metals are stored in water. For example, phosphorus is a very reactive non-metal. It catches fire if exposed to air. To prevent the contact of phosphorus with atmospheric oxygen, it is stored in water. Yet another important property of non-metals is that they do not react with acids. Let's look at this small experiment. Take some sulfur powder in a test tube. Add 2 to 3 ml of dilute hydrochloric acid or dilute sulfuric acid. There is no observable change. Unlike acids, bases do react with non-metals. The reaction of non-metals with bases is complex. For example, when chlorine reacts with a base like sodium hydroxide, it gives multiple products like sodium hypochlorite, sodium chloride, and water.
It was very interesting to learn so much about non-metals. Now, I will be able to identify the properties and uses of non-metals.
Rusty nails are common. But have you ever seen gold rusting? Gold never rusts, because unlike iron, it does not react with atmospheric oxygen. This is because chemical reactivity varies across metals. Scientists have arranged metals in a series based on their chemical reactivity. In this lesson, you will learn about the arrangement of metals in an activity series based on their reactive properties. You will also learn how the positions of metals in an activity series impact the process of extraction from their respective ores. You will learn in particular about the extraction of aluminium from its ores. At the end of this lesson, you will be able to illustrate through an experiment the differences in reactivity of metals. Analyze activity series of metals. Describe various techniques for the extraction of metals. Illustrate the process of reduction with examples. Describe the process of extraction of metals by electrolysis. Analyze the position of aluminium in the activity series. Describe the process of extraction of aluminium from bauxite. And list the uses of aluminium. You can observe the differences in reactivity of various metals through an experiment. Take samples of 4 metals: sodium, magnesium, calcium, and copper in different test tubes. Add 2 ml of dilute hydrochloric acid or sulfuric acid to each of these samples. The reaction of the acid with the metal will yield a salt and hydrogen gas in each test tube. However, you will notice that the rate at which the gas is liberated in each test tube is different. For instance, adding 2 ml of dilute hydrochloric acid to sodium results in a vigorous liberation of hydrogen gas. If you hold a burning splinter over the mouth of the test tube, the flame is extinguished with a pop sound. Similarly, the addition of dilute hydrochloric acid to magnesium in the second test tube liberates hydrogen. However, the rate at which hydrogen is liberated in this case is lower than that observed in sodium. The rate of liberation of hydrogen reduces further in the reaction with calcium, while copper does not react with hydrochloric acid at all. The variation in the rate of liberation of hydrogen indicates that the metals differ in their reactivity. To predict the reactions of given metals with other elements, scientists developed a system where metals were arranged in decreasing order of their reactivity. This arrangement of metals is called the activity series of metals. Thus, in this series, the most reactive elements are at the top and the least reactive elements are at the bottom. For example, potassium at the top of the series is the most reactive among all the elements in the series. For any two metals in the series, the metal placed higher in the series can displace the other metal from its salt solution. For example, zinc displaces copper from copper sulfate solution to form zinc sulfate. As you move down the series, oxides of highly reactive metals like magnesium and aluminium are not reduced easily either by hydrogen, carbon, or carbon monoxide. This is because the ionic forms of magnesium and aluminium are more stable than their atoms. Moving further down, metals that are placed below copper do not rust easily because of their low reactivity. A number of metals are available only in combined forms as ores. To obtain the pure forms of these metals, we need to extract them from their respective ores. Based on the reactivity displayed by metals, they can be extracted through the following methods: reduction and electrolysis. Reduction is the process of removal of oxygen for extraction of metals from their oxide ores. The common reducing agents used for reduction of metal oxides are carbon monoxide, carbon, hydrogen. For example, iron oxide is reduced to iron by carbon monoxide. Iron oxide is reduced to iron using carbon as the reducing agent. Similarly, copper oxide is reduced to copper using carbon. Copper oxide is reduced to copper using hydrogen. The metals high up in the activity series are very reactive. Hence, they cannot be obtained from their compounds by heating with common reducing agents like carbon, carbon monoxide, and hydrogen. For example, a reducing agent like carbon cannot reduce the oxides of metals like sodium, magnesium, calcium, and aluminium because they have more affinity for oxygen than carbon. Therefore, these metals are refined by another method known as electrolysis. Electrolysis is the process of the decomposition of a substance by passing electricity through it in a molten or dissolved state. Consider magnesium chloride ore. Magnesium is highly reactive and therefore cannot be reduced by common reducing agents like carbon, carbon monoxide, and hydrogen. Therefore, magnesium is extracted by electrolysis. Electrolysis of fused magnesium chloride gives magnesium at cathode and chlorine at anode. During the reaction at cathode, the reduction of magnesium chloride occurs due to gain of electrons. Magnesium ions gain electrons forming magnesium atoms. During the reaction at anode, chloride ions get oxidized due to loss of electrons. Thus, chloride ions lose electrons to form chlorine atoms. Chlorine atoms combine to form chlorine molecules. Thus, as a result of electrolysis of magnesium chloride, magnesium metal is deposited at the cathode, and chlorine is liberated as a gas at the anode. Let's now take up aluminium, a well-known metal in the activity series, and analyze its properties as well as the method for its extraction. Aluminium is a highly electropositive element and so forms positive ions. Therefore, it is placed towards the top and below magnesium in the activity series. It is not viable to use carbon reduction as a method for extraction of aluminium because the metal needs to be heated to very high temperatures in this method. Therefore, aluminium is extracted from its ores using electrolysis. Important ores of aluminium are bauxite, represented by the formula Al2O3 2H2O, corundum, represented by the formula Al2O3, and cryolite with the formula Na3AlF6. Bauxite is the principal ore of aluminium. The extraction of aluminium from bauxite involves 3 steps. First, the purification of bauxite using Bayer's process. Next, the electrolytic reduction of anhydrous Al2O3 by Hall and Herold's process. The last step is the purification of impure aluminium by Hope's process. The first step in the extraction of aluminium is the purification of bauxite through a process called Bayer's process. This process is named after Austrian chemist Carl Bayer, who invented and developed the method to supply alumina for the textile industry. Iron oxide is present as an impurity in bauxite. In Bayer's process, this iron oxide is removed by treatment of bauxite with sodium hydroxide solution. Purification of bauxite involves 3 steps. In the first step, aluminium oxide is allowed to react with sodium hydroxide to form sodium metaaluminate. In the second step, sodium metaaluminate is diluted with water to form aluminium hydroxide. In the third step, aluminium hydroxide is heated strongly to form aluminium oxide. The second step in the extraction of aluminium is the electrolytic reduction of alumina obtained using Bayer's process. This is done through Hall and Herold's process. Hall and Herold developed the process independently. The electrolytic cell used in this process has the following components: an iron tank lined on the inside with carbon, which acts as the cathode, a series of carbon rods that act as the anode, alumina, Al2O3, as the electrolyte. Fluorspar and cryolite are mixed with the electrolyte to increase its electrical conductivity and decrease the fusion temperature. In the electrolytic process, electricity is passed through the electrolytic cell. Sodium, aluminium, and calcium ions migrate towards cathode. The aluminium ions discharged at the cathode sink to the bottom of the tank and are periodically tapped off. The oxide ions lose electrons and form oxygen atoms at the anode. The oxygen atoms combine and form oxygen molecules. The metal obtained after Hall and Herold's process is about 98% pure. This needs to be purified further. The third step is purification of the electrolyzed output from Hall and Herold's process. This is done by using a cell developed by Hope. Therefore, the process is called Hope's process. hoop cell consists of an iron tank lined at the base with carbon, 3 layers of molten aluminium with different densities to prevent their mixing. The upper layer of the electrolyte cell consists of pure molten aluminium with a series of carbon rods that serve as the cathode. The middle layer or the electrolyte layer consists of a molten mixture of sodium, barium and aluminium fluorides. The third layer is the bottom layer. Along with the carbon lining, it acts as the anode for the electrolytic cell. The bottom layer contains impure molten aluminium obtained from Hall and Herold's process. Using this cell, aluminium is purified in 4 steps. Electricity is passed through hoop cell. Aluminium ions from the middle layer reach the top layer and get discharged. Aluminium ions collect at cathode as pure aluminium. At the same time, an equal amount of aluminium from the bottom layer, that is, the anode layer, moves to the middle layer. In this process, 99.98% pure aluminium is obtained. Aluminium is used in a wide range of products, from chocolate wrappers to sophisticated aeroplanes. Let's take a look at some of its common uses. Aluminium is widely used in the manufacture of automobile components because of its strength and relatively lighter weight. In the construction process due to its high tensile strength. In the manufacture of electric wires due to its high conductivity. For the packing of medicines and pharmaceutical products due to its malleable nature. In the manufacture of soft drink cans and espresso coffee makers because it does not rust and is relatively less toxic in nature. In the manufacture of kitchen utensils because aluminium is a good conductor of heat. Extracted aluminium in combination with other metals like copper, manganese, magnesium form alloys. An alloy is a homogeneous mixture of solid solution of 2 or more metals or metals with non-metals. Duralumin is a light and tensile alloy of aluminium. Duralumin is composed of 95% of aluminium, 4% of copper, 0.5% of manganese, and 0.5% of magnesium. Let us look at some of the common uses of duralumin. Duralumin is widely used in the aircraft industry. This is because of its lightness and other desirable physical properties. It is also used in making pressure cookers to withstand high temperatures. Magnesium is an alloy of aluminium and magnesium. Although weak and soft in elemental state, magnesium combines with aluminium to produce some alloys that are useful in engineering materials. Magnesium is composed of 85% of aluminium and 15% of magnesium. Magnesium is used in the making of balances because of its high structural strength and resistance to corrosion. It is also used in the making of optical instruments like cameras and microscopes due to its light weight and resistant to corrosion.
You already know that most metals are found in nature in a combined state. Metals that are found in a combined state in the Earth's crust are known as minerals. Not all minerals can be used to extract metals. Only the minerals that have a relatively high concentration of metal and can be extracted in an easy and cost-effective manner are used for extraction. Such minerals are known as ores. For example, bauxite is the principal ore of aluminium. The metal is extracted from the ore after a series of procedures and techniques known as extraction and isolation procedures. The main steps involved in the extraction and isolation of metals from ores are given here. Concentration of the ore, isolation of the metal from its concentrated ore, refining of the metal. The branch of science and technology that deals with the isolation of metals from their ores is known as metallurgy. An ore contains a metal associated with other andesite substances like sand, clay, etc. These andesite substances are collectively known as gangue or matrix. The process of separating gangue from an ore is known as concentration of the ore. It is also called dressing or benefaction. Metals can be concentrated from their ores using any of these methods: hydraulic washing, magnetic separation, froth flotation, or leaching. The choice of the technique used for extraction depends upon the differences in the physical properties of the compound of the metal present and that of the gangue, the type of metal, the facilities available, and environmental factors are also taken into consideration. Let's now look at each method in detail. The name hydraulic means operated by the pressure created by forcing water or another liquid. Washing ore with water is known as hydraulic washing. Gold mines make use of a hydraulic washing technique. An upward stream of running water is used to wash powdered ore. The lighter particles of the gangue are washed away and the heavier ore is left behind. This technique separates the gangue from the ore using the difference in their specific gravities. It is, therefore, also known as gravity separation. Magnetic separation is used when either the ore or the impurities in it are magnetic in nature. For example, separating iron from its ore, hematite. In this method, powdered ore is placed on a conveyor belt that moves over magnetic rollers. As the ore passes over the conveyor belt, the magnetic particles are attracted by the magnetic roller. The magnetic particles fall in a container below the roller, while the non-magnetic particles fall in another container that is away from the roller. Froth flotation separates the gangue particles from the ore based on the fact that gangue is wetted by water, while mineral is wetted by oil. The ore is crushed into fine powder and mixed in water. Then, collectors and stabilizers are added to the water. A collector is a substance such as pine oil or a fatty acid which enhances the non-wettability of the ore particles. A stabilizer is a substance like cresol which increases the stability of the froth. The mixture is agitated with the help of a rotating paddle. This draws air into the mixture and froth is generated. The froth is then skimmed off and is dried to recover particles of the ore. This is similar to the technique that separates butter from buttermilk. The froth flotation technique is mostly used for sulfide ores, as they are easily wetted by oil. It is also possible to separate two sulfide ores by simply adjusting the proportion of oil to water. At times, a depressant is used to separate two sulfide ores. A depressant is a substance that selectively prevents one of the ores from entering the froth. For example, if an ore has both zinc sulfide and lead sulfide, sodium cyanide is added as a depressant. It selectively allows only lead sulfide to enter the froth, but not zinc sulfide. Leaching is used when an ore is soluble in a certain suitable solvent. Let us consider the leaching of alumina from the principal ore, bauxite. The impurities associated with bauxite are silica and titanium dioxide. The leaching of alumina involves dissolution of the ore in concentrated sodium hydroxide at 473 to 523 Kelvin and 35 to 36 bar pressure. When the ore is dissolved in concentrated sodium hydroxide, the aluminium oxide reacts with sodium hydroxide and forms soluble sodium aluminate. The aluminate solution is neutralized by passing carbon dioxide gas. This precipitates hydrated aluminium oxide. The hydrated alumina is filtered, dried and heated to 1470 Kelvin to give pure alumina, that is, aluminium oxide. Another example is the leaching of silver or gold with a dilute sodium or potassium cyanide solution in the presence of air. Silver, when treated with dilute sodium cyanide solution in the presence of air, results in the formation of a complex called sodium argentocyanide. This, when treated with zinc, displaces silver from sodium argentocyanide and results in the formation of pure silver. Aluminium is the most abundant metal in the Earth's crust. In the Earth's crust, aluminium is found in the form of hydrated oxides like bauxite. Its chemical formula is Al2O3 2H2O. Generally, it contains some impurities like iron 2 oxide and sand. Metallurgy is defined as the process of extraction and further refining of metals from their ores. Primarily, 4 steps are involved in the process, namely, concentration of the ore, converting the ore into metallic oxides if the ore is not an oxide, reduction of the metallic oxides, and refining the impure metal. Bauxite, cryolite, and corundum are the main ores of aluminium. Bauxite is chemically hydrated aluminium oxide. Cryolite is sodium aluminium fluoride, and corundum is aluminium oxide. First, let's consider bauxite. The ore is concentrated by Bayer's process. The second step is converting the ore into metallic oxides. But this process is not required for bauxite as it is an oxide, Al2O3, and is also known as alumina. In the third step, alumina is reduced by electrolysis by Hall-Herold's process to form aluminium. Refining impure aluminium is the fourth step in the metallurgy of aluminium. It is done by Hoop's process. Through this process, 99.5% pure aluminium is converted into 99.9% pure aluminium. Now let's discuss the three steps in detail. The flowchart here gives you a brief idea about the entire metallurgy of aluminium. In Bayer's process, impure bauxite is converted into pure alumina by removing water molecules from it. The conversion process involves mainly three reactions. In the first reaction, concentrated sodium hydroxide solution is heated with amphoteric bauxite at a temperature of 150 to 200 degrees Celsius under pressure to get sodium aluminate. In the next reaction, sodium aluminate is diluted with water at a temperature of 50 to 60 degrees Celsius. Thus, sodium aluminate gets hydrolyzed to form solid aluminium hydroxide and sodium hydroxide. Note that as the precipitation reaction of aluminium hydroxide proceeds with the addition of a little amount of the same compound, the process is known as seeding. Finally, dried aluminium hydroxide precipitate is ignited at a temperature of 1100 degrees Celsius to remove water molecules to get alumina. The concentration of bauxite is also done through Hall's process, in which sodium aluminate is prepared by adding sodium carbonate to bauxite instead of sodium hydroxide. The reaction gives carbon dioxide and water as the byproducts. When excess carbon dioxide is passed through sodium aluminate in the presence of water, it forms aluminium hydroxide along with sodium carbonate. When dried aluminium hydroxide is ignited, alumina is formed. As already discussed, the second step of metallurgy, converting the ore into a metallic oxide, is not required in the case of aluminium, as bauxite is an oxide ore. The next process is the reduction of the metallic oxide into the metal. In case of aluminium, alumina is a very stable oxide, and aluminium shows a strong affinity to combine with oxygen. Therefore, reducing it with reducing agents is practically difficult. Thus, it is reduced by electrolytic reduction through Hall-Herold's process. In this process, alumina is heated with cryolite and fluorspar in the ratio of 1:3 1:1 by weight in an iron tank with a lining of carbon inside. Normally, alumina has a high melting point, and hence, cryolite with impurities is added in excess to reduce the melting point of the mixture. Once the oxide melts, a carbon rod fixed with a copper clamp, which acts as the anode, and a graphite object lined with carbon, which acts as the cathode, are introduced into it. Then, 100 amperes of electricity at 6 to 7 volts is applied. During electrolysis, metallic aluminium is liberated at the cathode and oxygen at the anode. The aluminium thus formed is collected at the bottom of the tank in molten stage and is taken out through a small outlet. During electrolysis, 6 oxide ions stabilize itself to form 3 oxygen molecules by leaving 12 electrons. These 12 electrons are accepted by 4 Al3+ ions to form 4 aluminium atoms. The table here gives the details of all the electron transactions during the electrolysis. The molten aluminium obtained after electrolysis is more than 99% pure and may contain less than 1% of impurities. The metal is refined by Hoops process to make it 99.9% pure. Hoops process uses electrolysis. In this method, electropositive aluminium is refined in a tank with 3 immiscible layers. Pure molten aluminium with a carbon electrode immersed into it functions as the cathode. This forms the upper layer in the tank. The middle layer is an electrolyte, which is a mixture of cryolite, barium fluoride, aluminium fluoride, and calcium fluoride. The bottom layer is of impure aluminium. The tank has a lining of carbon, which acts as the anode. When current is passed, aluminium ions from the electrolyte move towards the cathode, where they gain electrons to form pure aluminium. Then more aluminium ions from the impure aluminium in the bottom layer enter the middle layer to get electrons and get collected at the cathode. The bottom layer is replenished with impure aluminium at frequent intervals.
Zinc is the 24th most abundant element in the Earth's crust. Zinc occurs naturally in the form of sulfides and carbonates like zinc blende and calamine. Generally, these ores contain some impurities like iron 2 oxide and sand. In order to get pure metals from their ores, these impurities can be removed through a process called metallurgy. Metallurgy can be defined as the process of extraction and further refining of metals from their ores. Primarily, there are 4 steps involved in metallurgy, namely, concentration of the ores, converting the ores into metallic oxides if they are not oxides, reduction of the metallic oxides, and refining the impure metals. Let us study how zinc can be extracted from zinc blende. In the first step, the ore is concentrated by the froth flotation process. The second step is converting the ore into metallic oxide. In this step, the zinc blende is subjected to roasting at a temperature of 800 degrees Celsius. This results in the formation of zinc oxide with the liberation of sulfur dioxide gas. In the third step, zinc oxide is reduced to metal by using a suitable reducing agent such as carbon. It combines with the oxygen of zinc oxide to give zinc metal and carbon monoxide at a temperature of 1400 degrees Celsius. The zinc metal so formed is also known as spelter. The fourth step in the metallurgy of zinc is refining impure zinc. It is done by distillation or electrolytic refining. Let us now look at the physical properties of zinc. Zinc is a bluish-white metal. The density of zinc is 7.14 gram per cubic centimeter. Pure zinc is brittle at ordinary temperature. It is malleable and ductile at temperatures from 110 degrees Celsius to 150 degrees Celsius. Zinc is a good conductor of heat and electricity. The melting point of zinc is 419 degrees Celsius and the boiling point is 920 degrees Celsius. Let us now look at the chemical properties of zinc. First, let us look at the action of air on zinc. Like other metals, dry air does not have any action on zinc. But zinc reacts with moist air to form a white coat of basic zinc carbonate. Interestingly, when zinc is burnt in air, it releases bluish-white vapors of zinc oxide. Pure zinc does not react with either cold water or hot water. But when steam is passed over hot zinc, hydrogen is liberated along with zinc oxide. Let us study the reaction of zinc with non-metals. When zinc is heated with chlorine gas, it forms zinc chloride. Similarly, when it is heated with sulfur, it produces zinc sulfide. Unlike other metals such as copper and iron, zinc reacts with alkali to form zincate salts with the release of hydrogen gas. For example, Zinc reacts with sodium hydroxide to produce sodium zincate and hydrogen gas. Similarly, potassium hydroxide reacts with zinc to produce potassium zincate and hydrogen gas. When zinc reacts with dilute sulfuric acid, it produces hydrogen gas and zinc sulfate. However, reaction of zinc with concentrated sulfuric acid produces zinc sulfate, water, and sulfur dioxide gas. Similarly, dilute nitric acid reacts with zinc to produce zinc nitrate, water, and nitric oxide, while the reaction of zinc with concentrated nitric acid results in the formation of nitrogen dioxide. Zinc displaces metals from aqueous solutions of salts of less reactive metals such as copper and lead. Here, you can see how zinc displaces copper from an aqueous solution of copper sulfate. Finally, let us study the uses of zinc. Zinc is used for galvanizing iron. Galvanization is the process of coating iron or steel with zinc to protect them from corrosion. Galvanized iron does not corrode and is used to make pipes, roofs, I-beams, fences, and wires. Zinc is also used in the preparation of zinc white, a white paint. Zinc is extensively used in carbon zinc dry cells or batteries. Zinc forms alloys such as brass with copper, bronze with copper and tin, and German silver with copper and nickel. Brass is used in musical instruments, doorknobs, and ornaments. Bronze is used in utensils, jewelry, and photo frames. And German silver is used to make silver-plated cutlery, idols, and jewelry. In addition to all these uses, zinc dust is used as a reducing agent in the manufacture of perfumes and drugs.
You use many objects made of iron in your everyday life. Iron is an important constituent of hemoglobin, which is in blood. Iron is the metal used most widely in industries, and hence may be called the king of metals. It is a transition element denoted by the symbol Fe, from its Latin name, ferrum. It belongs to the 8th group and the 4th period in the D block of the periodic table. Its atomic number is 26 and mass number is 56. The electronic configuration of an iron atom is 1s2, 2s2 2p6, 3s2 3p6 3d6 4s2. Iron shows a variable valency of 2 and 3 in its compounds FeO and Fe2O3 respectively. Iron does not occur in native state since it is oxidized easily. It is available in ores such as hematite Fe2O3, magnetite Fe3O4, limonite Fe2O3H2O, siderite FeCO3 and iron pyrites FeS2. It is usually extracted from hematite and limonite. The extraction of iron from its ores involves 3 stages: concentration, calcination and reduction. Hematite is concentrated by the hydraulic washing or gravity separation method, while magnetite is concentrated by the magnetic separation method. In the hydraulic washing method, hematite is powdered and washed in flowing water to remove impurities such as sand, clay, and organic waste. These impurities are called gangue. In the magnetic separation method, magnetic separators are used for the concentration of the ore. A magnetic separator consists of a brass or leather belt moving over 2 rollers, one of which is an electromagnetic. Finely divided ore is dropped over the moving belt at one end. As the mass passes over the roller, the non-magnetic impurities fall from the magnetic ore and form a separate heap, while the magnetic component of the ore is attracted by the magnet and forms a heap near the roller. The concentrated ore is then subjected to calcination. Calcination is the process of heating the ore to high temperatures in the absence of air to remove impurities such as moisture, sulfur, arsenic and carbon dioxide. At this stage, the ore becomes porous. The calcined ore is then smelted. Smelting is the process of reducing an oxide with carbon in the presence of flux at a high temperature. Smelting is carried out in a blast furnace. A blast furnace is a tall cylindrical steel structure lined with fire bricks. It is about 100 feet high and about 25 feet in diameter. It has a double cup and cone arrangement at the top, through which the charge is fed into the furnace. A blast of hot air is blown into the furnace through water-cooled nozzles called tuyeres. The charge, which is calcined ore mixed with limestone and coke in the proportion of 8:1:4, is fed into a blast furnace through the cup and cone arrangement. A blast of hot air is blown into the furnace from bottom to aid combustion. The ore gets reduced by coke to metallic iron, which deposits at the bottom. A series of chemical reactions takes place in the furnace. Carbon dioxide is produced at the bottom of the furnace due to the combustion of coke to form carbon dioxide. As this reaction is exothermic, the temperature rises up to 1500 to 1700 degrees Celsius. As carbon dioxide rises upwards, it is reduced to carbon monoxide accompanied by heat absorption. Limestone, which is sliding down, decomposes to give lime and carbon dioxide. The lime thus obtained acts as flux and combines with silica to form calcium silicate. In the upper part of the furnace, iron oxide is reduced to spongy iron by carbon monoxide. At the bottom of the furnace, the molten iron sinks, and above it floats the fusible slag, which protects the molten iron from oxidation. The molten iron and slag are tapped off and collected separately through different outlets at the bottom. The molten iron withdrawn from the furnace is called pig iron. It is either converted into wrought iron or steel, or is cast into molds. Let's now look at the physical properties of iron. Iron is a grayish-white solid metal. Pure iron is soft and malleable. It is a ferromagnetic substance and a good conductor of heat and electricity. The melting point of iron is 1808 Kelvin or 1538 degrees Celsius, and boiling point is 3134 Kelvin or 2862 degrees Celsius. Let's now look at the chemical properties of iron. First, let us look at its reaction with oxygen and water. When iron objects are left in open moist air, iron reacts with oxygen and moisture to form rust or hydrated oxide of iron. When steam is passed over hot iron, hydrogen is liberated along with iron oxide. When iron reacts with dilute sulfuric acid, it produces hydrogen and iron sulfate. Iron is more reactive than some other metals like nickel, platinum, copper, and silver. Let's perform a simple activity to understand this. Take 2 new iron nails and suspend them in 2 separate beakers, one containing a solution of copper sulfate and the other a solution of silver nitrate. Label the beakers as 1 and 2. Leave them undisturbed for some time. After some time, you can see that in beaker 1, a brown coating of copper metal is formed on the iron nail and the blue-colored solution changes to pale green. Similarly, in beaker 2, you can see a deposit of silver metal on the nail. These reactions indicate that iron, being more reactive than copper and silver, displaces copper from the copper sulfate solution and silver from the silver nitrate solution. Now let's look at some alloys of iron. Iron alloys are very useful in various applications. The table here shows the components and uses of some alloys of iron. Stainless steel, which contains iron, carbon, nickel, and chromium, is used to make surgical instruments, cutlery, and utensils. Nickel steel, which contains iron and nickel with a little carbon, is used for making utensils and drilling instruments. Alnico is an alloy of iron, nickel, aluminium, and cobalt, and is used to make magnets. Invar, an alloy of iron and nickel with some carbon, is used to make pendulums. Nichrome is an alloy of iron, nickel and chromium, and is used for making heating coils. Steel, which is basically an alloy of iron and carbon, is used to make pipes, nails, sheets, and cutting tools. alloy is a homogeneous metallic solution composed of two or more elements. One of the elements in the alloys is essentially a metal, while the other element or elements may be metals or non-metals like carbon, silicon, sulfur or boron. Alloys are often made to alter the mechanical properties of the base metal. For example, to induce hardness, toughness, ductility, or other desired properties. Pure metals have poor mechanical properties. Hence, they are not used in their pure form in industry. Their properties are modified by adding other elements. Alloys are classified according to their components into three distinct types, namely ferrous, non-ferrous, and amalgams. Ferrous alloys are alloys with iron as the main constituent. The alloys also have other elements like carbon, chromium, vanadium, tungsten, and molybdenum. For example, carbon steel, alloy steel, stainless steel, tool steel, cast iron, and cast steel. Non-ferrous alloys are alloys that do not contain iron as a component. For example, alloys of aluminium, copper, lead, tin, titanium, zinc, nickel, cobalt, tungsten, molybdenum, magnesium, and precious metals. Amalgams refer to alloys of mercury with other metals. For example, dental amalgam, used in tooth fillings, is an alloy of mercury and silver. 24-karat gold is considered its purest form. Pure gold is very soft and cannot be molded into jewelry. That is why certain metals like copper or silver are added to it to lend it hardness and strength. To convert 24-karat gold into 22-karat gold, about 8.4% copper or silver is added, which decreases its purity to about 91.6%. Jewelry is mostly made in 22-karat gold. Let us now look at the characteristics of alloys. Some important characteristics are increased hardness, toughness, and corrosion resistance, inertness to commonly used chemicals, magnetizability, and ductility. The table here lists some important ferrous and non-ferrous alloys along with their composition and uses.